As to converting a decimal number to a binary number, we have two methods. The first one, method 1, works as follows. First step is subtract the largest power of 2 that gives a positive remainder and record the power. So for example, given number is 625 in decimal, then how do you convert it to binary? First, subtract the largest power of 2. So 512 is the largest power of 2, which gives the positive remainder. And then the power position is 9, so record 9. Now out of the remainder, we repeat that. 113, the largest power of 2 is 64, so remainder is 49, and the power was 6, so we recorded that. We keep doing so for 49. Largest power of 2 is 32, power is 5. From 17, 16 is the largest power of 2, power is 4. And from 1, the largest power of 2 is 1, and then now we have a remainder 0. So all these are power positions, and then we lay it down and place 1s when the power position appears in this conversion. So the resulting binary number is 10011110001. The ones are placed based on those power locations. So this is how to convert from a decimal number to binary. It's straightforward, but the problem with this one is when the number is huge, like a million or billion, then it is not easy to find the largest power of 2 intuitively. So when we have a small number, it is very intuitive to make it work. These are commonly occurring bases in digital logic design. So binary is the most frequent one as radix 2. We have 2 digits octal. We have radix 8. So we use 8 digits as follows. Decimal, we know that we use in daily life. Hexadecimal is radix 16. So we need 16 digits. So 0 through 9 is borrowed from numeric number digits, and then the remaining 6 we borrow from alphabets A through F, either uppercase or lowercase. These is numbers in different bases. So binary number, octal number, decimal number, and hexadecimal number. From 0 to 16, I want you to memorize it. We are going to use those conversions many times in many places. So it's a good idea to memorize this table as a computer organization student. Another method converting from decimal to binary, or of course to any other radix number system, is as follows. First, convert integer part, and then convert the fraction part, and then join the two results with a radix point. To convert integer part, for example, a binary number from decimal to binary number, then what you do is repeatedly divide the number by 2. And then save the remainder. That is how to convert integer part. And the fraction part is repeatedly multiply the fraction by 2 for binary number system. For any radix number system, integral part, so repeatedly divide the number by new radix. So fraction part, repeatedly multiply the fraction by new radix. That is the algorithm to convert from decimal to some other number system. So for example, the given number is 46.6874. To convert it to binary, first take the integer part, 46, and then repeatedly divide it by 2. So first divide it by 2, and then record the quotient and the remainder in separate columns. So don't do any fraction division. 46 divided by 2, quotient is 23 and remainder is 0. Take the quotient and keep divided by 2. So divided by 2 is a quotient 11 and remainder 1. Take the quotient 11 and divide it by 2. then quotient 5, remainder 1. Take the quotient 5 and divide it by 2, the quotient 2, remainder 1. Take the remainder 2, divide it by 2, then we have a quotient 1 and remainder 0. You take the quotient 1 and divide it by 2, now we have a quotient 0 and the remainder is 1. So we repeat this division process until we get the quotient 0. And then resulting binary number is from bottom to top in reading off in the reverse direction. So the 46 in decimal number is equivalent to 101110. For the fraction part, we apply a multiplication by 2. Take the fraction and multiply it by 2, and then record the integer part of the result. Here is 1. Next step, take a fraction part only, and then multiply it by 2. Out of the result, record the integer part. Take the fraction only, multiply by 2, and then out of the result, record the integer part. You keep doing so until the fraction part becomes 0. And then the result is reading off in the forward direction. So 0.6875 in decimal number is equivalent to binary 0.1011. So the converting the number is to join the result together with the radix point. So this is a resulting binary number equivalent to decimal number 46.6875. Here, to the fraction part, we have a few issues. The fraction part becomes 0, then we can stop the repeated multiplication. But in general, you may not have a fraction part 0. For example, converting 0.65 in decimal number to binary number, then you don't have a fraction part 0. But you will find some pattern repeats after certain points after the decimal point. So we have a repeating pattern forever. So solution is either to find a repeating pattern or just calculate up to certain digits after the radix point so that we can conclude the repeated multiplication. So once we got the conversion done, then you can convert it back to check whether the conversion was correct. So here 46.6875 in decimal, we have a resulting binary number, integer part here and the fraction part there. So for this binary part of a binary number, we can convert it back to decimal number by considering each digit in each position. Position has different weight. The very first one is at the 2 to the 5 in radix position. So that's a equivalent value of 32. So by adding those numbers with the consideration of a weight, we can convert it back to decimal number. Similarly, for fraction part, so each digit has a certain weight to some negative power. By calculating that, we can convert it back and then confirm the conversion was correct or not. Why do this repeated division works? Any number n can be represented with this way with the radix r. So red part is integer part and the blue part is a fraction part. As you can see, for the integer part, if you divide it by r first time, then the only item which cannot be divided r is a0. But any other part is divisible by r. So in the very first division, the remainder is a0. And then you take the quotient and divide it by r again, then the remainder is a sub 1, and so on. So repeated division generates for each step one coefficient at a time. For the fraction part, similarly, if you multiply by r, first integer part comes out is a sub minus 1. And the remainder part, if you take the fraction part again, then you get another digit and another digit comes on. So this is why the repeated multiplication for fraction part and the multiplication division for integer part works for converting from decimal number to any other number.